Okay, so the National Ignition Facility, as we said, making star power on Earth, and that's the goal. That's what we're going to talk about. And what we're going to be discussing is that technologies have been developed at NIF that offer a clean and abundant future source of fusion energy. We'll talk about what do we mean by clean, and what do we mean by abundant, and what do we mean by fusion. That is what the theme of the talk will be. Does everyone recognize this? Yeah, this is our sun. And the sun puts out enough energy in 1 second, just in 1 second, like, to fuel the Earth for 9 million years. So that's kind of an interesting concept. Now the question is there any way to bring that star power to Earth? Look how big the Earth is compared to the sun. This is actually real. Can you see that little dot there? You know, if you filled up the sun with Earths, it would take about 1 million of them to fill it up. The sun is a lot bigger than we are, and it's pouring out energy at prodigious rates. And when it does, it is providing for life on Earth. This is what our planet looks like. This is a nice summer day. You know, many pictures from satellites stitched together, and you can see it. See that white Sahara there that looks, those desert regions. See the beautiful Amazon and the Congo rainforest. And this is what it looks at night. And what is this a mark of, those lights? This is a mark of where we all live. And this is a mark of our civilization and what we do to our planet. What we do to our planet is, create energy in order to live better. And there's a couple of things that stick out on this when I look at it, which is, one is, a couple of places look very dense. You know, the United States. Does everyone see the United States? Right? It's got that big amount of energy. And if I look in Europe, right, Europe is all packed with energy. So the United States, Europe. Look at Japan. Japan is solid, right? It's about 120 million people in a small area, it's solid. And then we have two really interesting places, which are India and China. And India and China have around 2 billion people on them, which is around 40% of the population of the Earth. And they're underdeveloped countries and are growing very rapidly, and their energy requirements are huge. And that's where the future lies with respect to humankind's challenge, is providing for all of us a clean and an inexhaustible supply of energy. And because that is what provides the standard of living we have, and it also provides political stability and the like, and economic stability. Unfortunately, our planet's thirst for energy is increasing very rapidly. And if you look at it over the last 1,000 years, and I think I'll be showing you several things that go over 1,000 years, this is how it looks that our planet's requirements of energy have gone. Boom, right? So from 1,000, 1,200, 1,400, 1,600, 1,800, 1,900, it was just increasing very slowly. But then in 1900, it just blew out. And that is because, we were feeling the results of the Industrial Revolution. And humans were coming off their farms and into cities, and they were learning to build engines, steam engines, internal combustion engines. Manufacturing was happening, and the amount of energy we needed increased dramatically. And today we're climbing up this curve very rapidly, and it has great implications for our future. And the reason this is happening, the first order, is because world population is increasing. And if you look at that, same thing happened. Except that here it started, the world population increase started a little bit before the energy increase. And that's because around 1800, the germ theory started coming into play. People started understanding hygiene was important, clean water supplies were important, drugs started being invented, and you can see the implications of that. Right around 1900, again, population explodes, and that's what the energy needs exploded too. When you go back to that energy chart, the question that comes to your mind, you see it just expanding away from us at a high rate. How many more power plants do we actually need? And the answer is a lot. In the next 50 years, you have to think about the following. We need 2 new ones each week. right? And when I talk about new ones, I'm talking about big power plants, like 2 nuclear power plants per week, or 2 to 4 coal-fired power plants per week. And that means you're talking about 100 a year, and over the next 50 years, we're talking about 5,000 of them. This is an immense number of power plants and energy we will have to make. And what will they mostly be? They will be fossil fuel burners. Does everyone know what fossil fuel is? Yeah? What does fossil fuel have? Carbon, right? So when you look at fossil fuels like this charcoal, it's really a carbon-based activity. And if you look at wood, right? What is that? Mainly, it's carbon. And if we look at this fake can of gasoline, it's carbon, right? So we have fossil fuels, we have oil, we have coal, we have wood. These things are what we're going to be burning. And what is the good news about fossil fuels? It's cheap, and even when we complain about the price of it, it's just fair. It's around. If we, oil might be not as around as people want, but coal is just huge amounts of it in the world, huge amounts in the United States. But there's a problem with it, and the problem with it is what? Because it has the carbon. When you burn it, you make carbon dioxide, right? Right? And what's the problem with carbon dioxide? Well, I think we'll talk about it. It's greenhouse gases. If we look at what's happened to carbon dioxide pollution, again, during that same 1,000 years, it sort of looks like this. Right? Same thing, same exact story. As the population has grown, as our use of energy has grown, our carbon dioxide that we pump into our atmosphere grows up also. And this curve, by the way, is called the hockey stick curve. And I think you can see why if you've ever played hockey. It has a long handle and then a sharp stick at the end where it's going up. So if you ever hear about the greenhouse effect and the hockey stick curve, this is the one they're talking about. And you can see we're off the knee, we've turned up, and people are predicting that we could go up a factor of 3 over where we are now. Now there's a goal right now that if we work really, really hard to fight this, we could go up maybe a factor of 1.5. Most people think it's going to double in the next 50 years, and there's almost nothing we can do about it. We have to be thinking 50 years out to solutions that are going to come our way. This is a challenge for our species. What is the greenhouse effect? And I'll get back to carbon dioxide in a second. Greenhouses can be useful, of course, right? If you want to grow plants in a cold area and keep them warm without spending a lot of money on fuel, you can just put a plastic or glass container over your plant life. And what happens is sunlight comes in and it's absorbed on the ground and in the plants. And when it re-emits that energy, it's in a different color. So it re-emits infrared light. Infrared light is far to the red. And even though this plastic looks perfectly clear, in the visible light, it actually looks black to infrared light. So what happens is the infrared light goes up, it's absorbed, it doesn't leave the greenhouse, and it sort of keeps it warm. And that's what the greenhouse effect is. And it can be extremely useful, as in greenhouses. It also can be harmful, and this is something I think you all have experience with. When you park your car on a nice sunny day, right? And it might be 80 degrees, like it might be later this afternoon or in a couple of weeks, right? The car will be at the same temperature inside as it is outside to first order. But what happens is it sits out in the sun. That sunlight comes through the windows, right? It's absorbed inside your car. You've generally closed your windows so there's no convection or air exchange. And now infrared light is coming in. It can't go out that glass window. It can't go out the roof. You've built a greenhouse. And what happens? The temperature goes up. And so does everyone have that experience when in a summer day you leave your car and the air conditioner on, it was 70 degrees when you left it, you come back, you can't even touch the steering wheel, it's like a blast furnace? We all relate to that, right? That's the greenhouse effect. And so we have used to that. So we have good greenhouse effects, bad greenhouse effects. Which brings me to the story of Goldilocks and the Three Bears. And this might not sound like it has anything to do with the greenhouse effect, but in fact it does. And remember when Goldilocks when the bears came back and they found that when Goldilocks was talking about her porridge, Daddy Bear's porridge was too hot, and Mommy Bear's porridge was too cold, and the baby bear's porridge was just right. Well, if we look at our solar system, it's the same thing. If we look at Venus, Venus is a planet that's right next to us, has a very thick carbon dioxide atmosphere. And what is it about carbon dioxide that's interesting? Well, it is a greenhouse gas, which means it absorbs in the infrared. So any sunlight that gets through and heats up the surface of the planet, when that heat tries to get away from Venus to go out to space, it gets absorbed by the carbon dioxide in Venus and just keeps it hot. And because of that, Venus is really hot. It's around 900 degrees. So no life could live on that. So, in the words of Goldilocks, this porridge is way too hot, right? If you go to Mars, which is another planet that's right near us, right? Mars has almost no carbon dioxide. Has a little bit, but its temperature is around minus 80 degrees. And the reason it's so cold is as the sunlight hits the Mars surface, it heats up. There's very little carbon dioxide or greenhouse gas, so the energy just radiates out into space, and the place is freezing cold. In the words of Goldilocks, this porridge is way too cold. But our Earth, which has a very nice blanket of carbon dioxide, a few hundred parts per million, is just right to hold the temperature of the Earth at around 60 degrees, which is comfortable for all of us, and it promotes the planet's climate that we're used to and has generally been kind and forgiving to us, at least over the last 10,000 years since the last ice age retreated, and when our civilization was created. So for now, we're just right. If you look at Venus, what would happen, and if we can go back one view graph, Earth, we don't want this temperature to go up much, and it will go up because of carbon dioxide loading in the atmosphere. And if we did, we can see stuff like Venus. Of course, it won't get to Venus, but a few degrees would be a big deal to us in terms of the glaciers and our ecosystems. So let's go forward and think about what we want to do. Now, this might seem a little bit out of order, but let's just stop for a second and think about energy and power. Because to understand what's going on, the balance of the flow of energy and power into our Earth system, let's think about it in ways that we can think about it. People also have energy that has to be put to work. If I do this, I do work, right? I expend energy, right? Everyone knows, because when they run, they expend energy faster. It's power. They're expending power. If I do it faster, it is tiring because I'm spending the same amount of energy in a shorter period of time. My muscles have to burn faster. I sweat more, and we see where we're going. Does everyone think about when they're eating calories, like what that means? They say, most of you, especially younger people, don't count your calories, but it's around 2,500. There's another way to measure energy, and that's called joules. The reason I bring up joules is because when you all grow up to be famous scientists, you won't measure energy in calories except when you're eating it. You're eating food, you'll measure it in joules. We need around 10 million joules per day to live. When I say joules, I don't mean Joule. I mean James Prescott Joule, who was a famous scientist who lived in the 1800s, and he actually figured out how to measure energy. Now, as I said, the faster you do energy, you expend energy, the more power you need. So when we walk up a hill versus run up a hill, are we doing more energy or more power? Well, we actually are, if we just measured it as an engineer, we would say we're doing the same energy but expending more power. And it depends on how fast you're doing it. So when he's working out, he's expending a lot of power. course, you notice his face doesn't move. We didn't do that. And he gets hot and sweats. You know, and we call that power expenditure watts. So when you talk about watts, you hear the word kilowatt hours. You know, watts is how fast you're expending energy. Food gives us energy. Now, the reason I bring this up, you know, it sounds like, well, what does this have to do with global warming or the like? You know, we are, if we look at ourselves as scientists or engineers, we're just sort of crummy internal combustion engines. You know, if you look at your car going down the street, you put gasoline in it, right? And it burns. And when it burns, we have carbon dioxide and water coming out the back, right? If I take, you know, an M&M and I eat it, I love M&Ms, by the way. You know, what happens? I'm going to burn that also in my body. You know, and what's going to come out of me? Well, let's not get all of the things that will come out of me. But out of my mouth, I'll get what? Carbon dioxide, water vapor, right? That's what I'm doing. It's the same thing. I'm an internal combustion engine of a sort. You know, food gives us energy. And I wanted to show you, let me just show you this. So you get the size of joules. Here's some sugar crystals. Let's see if we can hold this steady enough. So these are, you know, brown sugar crystals. They're pretty big, chunky ones. Can you see them? Each one of those sugar crystals is 3 joules of energy. Okay? If I put an M&M on it, just want to show you that, that's around 18,000 joules of energy. If I put an apple here, well, let's see if I can do that. This is around 200,000 joules of energy. So if I take a bite of an apple, which is about 1/10 of an apple, it has about the same energy as an M&M. So when you're eating your M&Ms or your candy, think about, you know, the wasted calories you're getting. You're just packing yourselves in with junk. You could have a great apple and then get more in your mouth and be happy. I want you to keep these numbers in mind. Joules of energy, 200,000 joules in an apple. Okay, now when we expend energy, we have watts. So when I'm just sitting here, I'll stand here very quietly for you, and I'm going to put these light bulbs that are pointing towards you. Okay? Now these are 100-watt light bulbs, right? What do you think I am as a light bulb? Just standing here, believe it or not, my little internal combustion engine that's going all the time is burning about 100 watts. So I'm not as bright, and probably you can take that word any way you want, but these are light bulbs that are just putting out the same amount of energy. Anyway, I'm a light bulb in terms of power, and I just want you to remember that's 100 watts. So standing here, I'm 100 watts. So now we want to do a demonstration and to see how much power we can generate. Okay, so we have 2 volunteers, and Rick Sawicki is going to introduce them.
Hello, everybody. How are we doing so far? Do we have lots of energy out there? Lots of energy? Okay, we're going to have a demonstration of power. Okay, and power is how fast we use or expend energy. James and Nicole, step out here in front of the stage, please. James and Nicole are both from San Ramon, and they go to Cal High. And so if you could please sit down on the bicycle. Okay. Now, as they pedal, they're going to be turning an electrical generator. So why don't you both get started right now? And if we're lucky, the power meter will work. Pedal. The faster you pedal, the more power they will generate.
Come on,
and so we
faster,
see now
guys.
that Nicole is up to 40 watts, James is up to 120, 103, and getting tired.
Come on, let's go, faster.
Lance Armstrong puts out 900 watts. We're up to 75, 145 for James. Okay, thank you very much. That was great.
Okay, wait. Okay, so let's go over it. You know, I think that Rick said a couple of things. First of all, you see they did around 100 watts, so they could do as much energy as, much additional power as a light bulb, right? And you can see the light bulbs lighting up. But if I just want to have this a very embarrassing comment, how much energy did they expend doing that? Here's your M&M. And you didn't even expend that much. So when you're eating, think about working it off on doing exercise. It's hard work. So just think Lance Armstrong can do 900 watts for hours on end. And I think that you want to talk about what phenomenal athletes can do. That's how you can do it. Okay, we're going to do our karate demo. Now you can see that was sort of average, you know, power that you expended over a period of time. Now we're going to do something that's really quickly. And the faster you do work, the more power you create. Yeah. So when we talk about NIF later, that'll be something really important to understand, because NIF happens in billionths of a second. Wait, so we have to introduce ourselves?
Yeah, I would like to introduce Maxim Umansky. He's a plasma physicist at Lawrence Livermore Laboratory, and he's going to give us a demonstration of how you can take a certain amount of energy that you have in your body and compact it into a very short period of time and create a huge amount of power. Okay, and to demonstrate that, let's do it. Try to break this board by applying power to the board very slowly. So Maxim, could you stand on the board and press down on it? So when he does that, the board doesn't break. Okay. Now, using his muscles, he's going to take stored energy in his body and try to break that board by moving his foot very, very fast and breaking the board very, very, very quickly. Okay, a little bit of silence so that he can concentrate on this, please.
Whoa.
Yay, thank you.
Okay, so let's think about that. Was that a lot of energy or a lot of power? Well, the only thing he did, he was lifted up his foot and put it down. That's not much energy. I can do that, right? Now, if you put it down really quickly, it really doesn't take a lot more energy. It takes a lot more power. And how much power did Maxim create? We think, you know, we're not positive, but it's somewhere between 100,000 watts and 200,000 watts. Now, remember this light bulb? This light bulb was putting out 100 watts. These bicyclists put out 100 watts. So he was doing about 1,000 times more power in that very short amount of time. And when he did do that, he was doing as much power as a car speeding down the road. But it was only for a very short amount of time. So for around 100th of a second, whack, you could do that. And because of that huge power impulse, we have a broken board. Whereas when he just put the energy into it, nothing happened. It's really important to keep those things separate. Let's talk about balloons. Thank you very much. Okay, I want to do some work. I'm going to use some energy from my body. Now, remember, I'm a CO2 producing machine. I'm helping the greenhouse effect get worse right now. I'm telling you, we've done a calculation, and we've done about 1 joule. I just did about 1 joule of work. Now, I want to just let go of this and watch the air come out of here. And well, let's estimate how much time it takes for it all to happen. What do you think? Second, 2 seconds? 4 seconds? 3 seconds? So we were doing about 1 joule of work in, say, 2 or 3 seconds. So it's like a half watt. Now, does anyone have anything in their brains that goes at a half watt? Right, your phone is about a half watt to 1 watt. So it's putting out about that much energy, that much power, excuse me. Now, Rickster, we have the same balloon, so we did the same amount of work. This is the same thing as that karate chop, right? What I'm gonna do is now why was it so loud? Because we've expended a lot of power real quickly, right? And so we've taken that 1 joule that was putting out 1 watt and probably created over 100 watts. I just want everyone to keep those things in mind as we go through this talk. And let's talk about our Earth now. How much energy does it take to provide our planet electrical needs for 1 year? Now, we were talking about, joules. This is a few thousand joules, right? The Earth takes 500,000 joules of energy, right? That's a lot of M&Ms. Another way to say that is that we have a million, so it's 500 million joules of energy. The word, by the way, is quintillion. Why that word exists, I Googled those words and I couldn't find out why that word exists. Does anyone know what the Google is? Well, the number Google, does anyone know? What do you think? How much? Yeah, it's 100 zeros, the word Google. Does anyone know what a Googleplex is? You know what a Googleplex is? Actually, it doesn't have Google zeros. It's a Google raised to the Google power. If you can figure out how many zeros that is, you should bring it into your math teacher. It's a very big number. Okay, so that's what Google is a real number. Okay, so how much power does it take to provide for our Earth's electrical needs? You saw how much energy we use in a year, but how much of power are we using all the time? And the answer is 15,000 watts, which is 15 million watts, or 15,000 billion watts, or 15 trillion watts. Does everyone know all those numbers? You know how to do that? You count those 3 zeros, those are thousands, 6 zeros are millions, 9 zeros are billions, 12 zeros are trillions. Okay, you got it? So we use 15 trillion watts of power. How many bicyclists would it take to do that if they were doing 300 watts, which we can't do? It would take 50 billion bicyclists, enough to circle the Earth tire to tire 2,400 times. Humans are not good animals for doing this. Do you think, who was doing that bicycle riding? Can you guys stand up? Do you think you could do that 24 hours a day? No, they could do it for a few seconds and then they puckered out. Okay, what's the clue to our future, right? If we don't want to burn carbon dioxide, we have to look to, the source of energy that provides no carbon dioxide, and that's the sun. And the sun puts out this huge amount of energy, and it puts it out all the time. Who figured this out?
Theory of relativity that mass and energy are but different manifestations of the same thing. Furthermore, the equation E is equal mc squared, in which energy is put equal to mass multiplied with the square of the velocity of light, showed that very small amount of mass may be converted into a very large amount of energy.
So the story is that Albert sort of came up with this equation that, of course, Homer thinks he could have thought of it, but he never got the C part. He had B's and E's and G's and D's. He never got the C squared right. But the thing that Albert said is that the energy in mass the energy and mass are the same, and they're related by the speed of light times itself. Speed of light is a very big number, right? It's 300 million meters per second, or 186,000 miles per hour. If you put that times itself, that if you could turn this is a little bit more than a kilogram, into energy, you would have 90,000 joules. It's more than 100 million times more efficient than chemical energy that's stored in an apple or in sugar. And that's why people were really interested when Einstein thought of this. It's a remarkable thing. If you could turn this amount of water, you see this up here, right, into energy using equals mc squared, we'd have as much energy as is in a super tanker full of oil. But there's one thing we wouldn't have, and what is that? What happens when you burn oil? You get carbon dioxide, right? If we had a nuclear burn of water, we would not get that. But E equals mc squared is alive and well on our Earth right now. It's the basis of nuclear energy. And when you hear about nuclear power, when we talk about fission, splitting uranium atoms in half, that's what's going on. We're making mc squared energy. E equals mc squared powers the cosmos. Everywhere you stare up into space and you see bright light, from stars, supernova, galaxies, clusters, the sun, it is because of E equals mc squared. I think it's really important that we can create, what's going on the sun, for you to understand, is that we're creating energy from matter. The sun is very hot, over 15 million degrees centigrade, which is around 30 million degrees Fahrenheit. Very, very hot. That would be a hot day. And it also compresses huge pressures. It also creates huge pressures that could compress matter to densities much greater than lead. In fact, in the sun, the density of matter is around over 100 times that it is on the Earth. So if I had this big pile of water, I'm not saying it wouldn't evaporate, but just imagine, and I could take it into the middle of the sun, it would be this big, right? So that's what happens. You have matter that's really hot and really compressed. And that's a very unusual condition for matter. And when it happens, you can take atoms of hydrogen and fuse them together and do E equals mc squared work. That's what we're doing at the National Ignition Facility. And our goal is to create those kind of temperatures, actually higher, those kind of pressures, actually higher. We're going for 100 million degrees, and pressures that we get 1,000 times the density that we have on Earth, and put them into this target. And we put them into this target, we hope that we can create the conditions that are in the sun. And when we do that, we can get fusion energy. So we can bring the sun to the Earth in a very small scale, of course, but let's talk about that. One of the things I wanted to show you was a real target. Mimi, are you here or not? Okay, so we'll see if I can hold this steady enough. I mean, maybe you can just look at this picture, but this will give you another view of it. I wanted to show you the inside of it. I'll hold it as steady as I can. Can you see it? So right up there, you can see those blue lines, because I can't look at them. You have to tell me if I got it. And those blue lines are where the laser light goes into that gold can. By the way, this is not exactly solid gold, but pretty close. And here's what a target looks like, and here's that little ball on the inside. Here's the laser beams coming in. I'm going to stop it for a second. And what you can see is that this gold can is starting to get very hot. In fact, it goes up to a few million degrees in a few billionths of a second, right? That's how long the laser is on. And when it goes on, it gets super hot. And does everyone know what happens to an oven when it gets hot? Whoop, let me do that. It starts putting energy onto your cake or pie or roast and cooking it. In this case, we cook this little target in the middle. And when it does, it implodes. And you can see it's getting smaller and smaller. And remember I told you we were trying to create high-density matter? This is getting high density, right? We have the same amount of matter in a smaller and smaller in space. Look how small it's getting. When it gets to around 1/10,000th of the volume and about 100 million degrees, those atoms inside will fuse together and burn. And that's where we have. And this, let me just go over the time scale. That all happened in a few billionths of a second. And the burn happens in a few trillionths of a second. These are not numbers or time scales we normally run into in our everyday life. So if you're a scientist at the NIF, something like a millionth of a second is like centuries. And a billionth of a second is normal. Trillionth of a second is pretty fast, but things are moving along at high speeds. So let's talk about, we have that little tiny target, but we have this really big laser. It's big enough to have 3 football fields on top of it. And there's 192 beams that are transported to our target chamber. And the way that we do that is like this. Let me take the roof off through the magic of CAD. we have a little laser that goes into the big laser bays, and now it's low energy, it's low power, but we send it through these amplifiers that I'll talk about in a second that make it high power, and now we come into our switch yard. Remember that you saw that those little, could you see those blue beams, and you could saw it, they come in sort of radially like this? So we have to take all these lasers and this big facility and get them into that little target chamber like that, right? Does everyone know what polar geometry is? Yeah, so there's square geometry or rectilinear geometry for those of you taking geometry. Some of you probably will take polar geometry, other kinds of geometry where you just look at things on a spherical basis. Now you watch what happens, and here they come in. So now you can see they're headed in, and they look like they're going in spherically, and bam. Okay, so let's look ahead. So that's what a NIF laser bay looks like. And here you can see 96 of the 192 beams. Even though there's no people in here, just to give you a feeling, this is probably about 5 times the size of this auditorium in length. And it's about probably 50% wider. And the laser beams are transported to this area where we have the target chamber. That's what the target chamber looks like. If any of you, when you're walking out, look at the first target chamber we have, it's out on the front from the 1960s, it's this big. This thing is 40 feet tall. So, you know, it would just fit inside this room. Sort of fill up this room pretty much, right? That's how big that target chamber is. And this is how it looks like when you go inside of it. And this is the really inside of it. So you get an idea how big it is. See that human standing there? His name is Vaughn Dragoo. He's 6'2". So you have an idea of how big the target chamber is. And also, this is how we hold that. Remember that little target? We hold it right in the middle, you know, vertically like this, and the laser beams come in on it. Now, remember, the reason we're doing this is because we want to get real high energy in a really short time. But we have to start at a very small place. And believe it or not, the beginning of the laser is only the size of your index finger, where it says DFB laser. What we have to do is get it to high power. And let me just talk about how we do that. Here's one of our amplifiers. Now, you're used to amplifiers in your life all the time. You know, whether it's in your phone or wherever. We're going to do some amplifier experiments, but this amplifies light, not sound. And I want to do a sound experiment too, so we can talk about it. So let's first of all do some experiments. Has anyone ever done the clapping experiment with me? Well, let's just do it. Everyone just clap. Let's just all clap. Thank you very much. Now, I want you just to clap normally, and when I say clap together, which I mean synchronously, just clap together. So when I'll tell you, just start clapping. Okay, together. Now, isn't that remarkable? You know? Now, that's called going from a noise condition to a coherent condition. Now I'll just do another experiment. Let's just clap with 2 fingers. Okay, now try to lock up. A little bit harder, but we can do it, right? Okay, now let's just try 1 finger. Shh. Okay, do it. Try to lock up. We can't tell, right? Because it got too quiet. So we can't come out of that noisy condition because we don't have enough feedback, sound. Now I want to talk about, now that we have coherence, does everyone understand coherence now? That's what a laser light is. It's coherent. It's all those sound waves, light waves marching together. Now we're going to do amplification. So I'm going to ask some members of the band, let's try one of them, all the way over here on the right, to start clapping, and then let's amplify the sound. Let's just listen for a second and then lock up with them. Okay, so you now know everything about lasers. He is the master laser, and you are the amplifiers. You know, you were not only made him louder, but you made it coherent, right? So one more time, let's do it with 2 fingers now. In fact, why don't you just do it with 1 finger, but you guys can clap. And you guys just listen and just spread the word, okay? Rest of the band, get going. Okay, so even though you guys didn't know what the first laser was doing, right? You couldn't hear him at all. Pretty soon, the rest of you picked up on what was going on. That's how a laser works. So when we go back to this master oscillator here, that's him. Then we go to those guys, those are the preamplifier. And then we go to the big lasers right here, and that's the big amplifiers. Now we're going to do one more demo because we also have another experience with sound. Let's do, where's Tom? Is he there? Okay, so he's going to now play the guitar without his amplifier on. Can you hear it? Yes. Not much though, it's pretty quiet, right? Now let's put on a little power there. Let's really crank it up. Okay, so what he's doing is taking electricity from the wall to amplify a sound. Lasers are doing the same thing, except we don't store energy, we don't store electrical energy. Here's some laser glass. We store light energy. This is kind of incredible. So when you look at your regular glass, you know, like clear glass, does it work at all as a laser? Not exactly. But this stuff has some really interesting material in it that stores optical energy or stores light energy. There's neodymium in it, and that's why it's such a great laser. We have about 3,000 pieces of this in the NIF. They're a little bit bigger, about that big. So we have a lot of glass in the NIF. Okay, so we got that, so you guys understand amplification. And just gives you a feeling about how big those amplifiers are, right? See Venus standing there? She's around, she's a little under 2 meters tall. Does everyone know meters? Meters a little over 3 feet, right? And here's something interesting. A single NIF, and I want you to think about this because we're going to play Jeopardy or Geoenergy soon. A single NIF laser pulse produces 33 times more power during the billionths of a second it's on than the whole power demand for the Earth. Now, it doesn't make that much energy, but it has 33 times the power. And a fusion experiment will release, listen to this one, 20 quadrillion watts of power in less than a billionth of a second. So when we really light this sucker up, you know, we have hundreds and thousands of times more power than is being created on the Earth during that time period. And that's why it's so interesting to us to figure out how to do this. Because what is the thing that is happening here? We're burning nuclear matter being hydrogen, which is water. And are we making anything else? No, no carbon dioxide, sulfur dioxide, or anything like it. The stars made in NIF will establish the basis for our fusion future, or so we think, so we hope. This is one of our goals. Fusion as a future energy source could be crucial to the world as it develops. Now, the question that we have is, can NIF technology be adapted to do an electrical power plant? I love NIF, and I've worked on it for a long time, and some people in this room have too, but it has one problem. We only can fire it once about every 3 hours. You remember how Billy got tired from spending too much power because he overheated and blah, blah, blah? Sort of in a very crude way, that's what happens to NIF. It can't go very often. And we have to figure out how to make it go very often, like a few times a second, in order to make it a fusion energy plant. We have some really interesting ideas how to do it. They sort of look like the NIF, actually. They're not much bigger than the NIF, and they might be smaller. And they're based on a target chamber that's very similar to the NIF. So we're testing all the physics of it. And it's a part of a long series of lasers we've been building since the 1970s that have gone up from 100 joules. Now that you know what a joule is, 100 joules is how much? A few grains of sugar. Doesn't sound like a lot, but when you put it into a billionth of a second, it can do a huge amount. to megajoules. And we're looking to do this. You know, remember, once we want to fire the laser and get it that fast, right? So we want targets going off like that. Now, that's a challenge, right? So remember, right now we're doing it once every 3 hours. So we could fire it now once, and if we were lucky this afternoon, we could come back after lunch, fire it again. This is what we're trying to do. So this is what engineers and scientists at the lab are thinking about right now. Now, it isn't that we're just dreaming. We're developing lasers that can do this. I want to show you a laser that's not exactly made for this, but we're looking at a laser that's illuminating a piece of steel. And watch what happens when I turn on the laser. We're just blasting steel away. You might not like that noise, but we love that sound. Okay? So, you know, I can just do it again. Right, I'm going to try to do it again. And this is the idea. So if you want to make lasers that can go that fast, you have to think about this kind of capability. And we're developing it right now at the lab. It's an opportunity that we think we have. Okay, time to play geoenergy. Okay, I want to tell you some things about geoenergy. Here's Alex Trebek, and he's going to introduce it. You know, I just want you to know that in the first show that we had this morning, you know, some of the audience thought these questions were too hard and unfair. But I had the feeling as you were walking in that your IQ was generally higher and your attention span was much better. And we're going to see how you do.
Okay, are we ready to play geoenergy? Okay, so we have 6 contestants here. And I would like to introduce the first two, who are Rumus and Vanessa. And Rumus and Vanessa, where are you from? Just speak into the microphone, please.
Livermore.
They're from Livermore. Very nice. And then we have Niharika and Shivangi, way down in the end. And you're from where?
San Ramon.
Okay, speak close to the microphone.
San Ramon.
San Ramon versus Livermore. This is going to be a very nice contest. And then we have Terry and Allison. And you're from?
Pleasanton.
Pleasanton, perfect. We have the 3 cities of the Tri-Valley here represented, and we can start asking questions now. Each of them will have a horn that they can blow when they know the correct question, and why don't we give that a test to see if we can do that. Everybody? Now, does anybody know how many joules of energy do they expend? Take a guess. I think 3's about right. Okay, Ed, you can.
So you guys are getting the whole idea. Okay, so geoenergy. Let's go to look at our categories and talk about them. We have 6 categories: energy and power, power plants equals MC squared, Albert's favorite, lasers, my favorite, human beings, chemical energy. So I'm going to be asking the questions. You don't get to choose, but you're going to have to look up here. So our first question is, in energy and power, a household for 200 joules, a household item that uses 60 watts.
What is it, light bulb?
Exactly, let's hear it. What is a light bulb? 60 watts, and she gets that exactly right. Your name, please?
Shivangi.
You got it. Okay, next question we're going to ask is, let's take a good question here. Human beings, for 400 joules, uses 300 watts pedaling fast down the road.
What is a bicyclist?
Yes, exactly. What does a bicyclist use? And you can see a bicyclist, you know, can use around a good bicyclist, not anyone we had here. It could do about 5 times the power expenditure of a 60-watt light bulb, but not for long. Okay, the third question is, let's see what categories. Power plants uses uranium to generate 1 million watts of electrical power, a gigawatt of electrical power.
What is a nuclear power?
Exactly. What is a nuclear power plant? Now, what were the rest of you thinking? What else uses uranium? Okay. Okay, let's look at where nuclear power plant sits. A nuclear power plant goes up to around 1 billion watts. By the way, that's called, so you know, for your friends and enemies, a gigawatt. G-I-G-A. So if you ever hear that term, gigawatt, that's what it stands for. Now, if you go to England, you'll hear the term gigawatt, but it's the same thing. Okay, let's go on to our next question. Our next question is energy and power, 15,000 watts. 15 million watts.
How much energy the Earth uses?
How much energy does the Earth use? Okay, we're going to have to go to the judges for a ruling on this. Does anyone think she got that answer right? Anyone who thinks she got it right, raise their hand. Anyone who thinks she got it wrong, raise their hand. Okay, let's hear from the wrong people. What do you think the answer is? It says, what does watts measure? Does watts measure energy or power? Power. So I think the answer is, we'll give them half credit. And it's really how much power does the Earth use, right? Not how much energy. So I think it's important, you know, that we all keep those things straight. Okay, let's have a round of applause for half hour. Okay, and you know, when you look at that, the Earth uses, this is kind of interesting, you know, if we put that on the stage, we go from 1 billion to 1 trillion. So if you had, just to go over this, if we had 15,000 nuclear power plants, that's all it would take to run the Earth. And our next question is lasers, 33 times more power than the Earth uses. Now, I told you the answer to this, very explicit. Remember, the category is lasers. Okay, let's answer your question. Ask your question very carefully.
How much power does one laser at NIF produce?
What do we think, guys? In a single pulse, right? I think that's full credit. Okay, so just think about that. If you think about that, it's kind of blows my mind. I work on NIF every day, and when I think about that, I say, during that few billionths of a second that the laser pulse is on, we're creating 33 times more power than the whole world is using during that time. But of course, it's mostly off, so we can't use that to run the world. Okay? And for our last question, okay, we talked about this, 200 quadrillion watts released in less than 1 billionth of a second. Now this is the hard one. No one got this on the last one. I think we answered this. Did we give this information? Yes. You guys got it? It was.
How about we give them? How about a clue? What happens inside the NIF facility?
Okay, blow away.
Fusion.
Okay, so fusion is right. 200 quadrillion watts is released in less than 1 billionth of a second in a NIF fusion implosion, right? So I just want you to know, you guys have all the answers and questions in your cheat sheets there, but that's the thing we have. So let's hear it for that. 200 quadrillion watts, where does that fit on the scale? You know, this is again another factor of 100 above, you know, where the Earth is. This is really kind of a remarkable thing. So if you can make it happen a few times a second, you can create energy and power that are enough to do it. So let's look at the final score here. It looks like Livermore really was pretty impressive. 1,200 joules for Livermore. 200 joules for San Ramon, and 0 joules for Pleasanton. But let's face it, we're in Pleasanton and they've been great hosts. What are our prizes for the...
Okay, for our winners, we actually have 400,000 joules that we'd like to give to the winners. And for participating, we have 200,000 joules. Thank you very much. And for, was that Pleasanton down here? San Ramon, 200,000 joules. And Slinkies for all.
Thank you very much. Let's hear it for our contestants. Okay, I want to end this talk, just to talk about things. Fusion energy is a big problem and it's a big challenge, and it's going to take a little while to get it together. And it sort of started in the 1950s, and it's my belief that it'll be commercial in the 2050 time period, which is like 40 years from now, right? And so it's sort of like a 100-year problem. People say, gosh, 100 years, how do we deal with that? Well, the answer is we deal with 100-year problems all the time. In fact, I think the history of aviation is something that we all should think back. Aviation is a 100-year-old industry right now. You see on the left, the Wright brothers were just starting up in 1903. That plane flew on its maiden flight less length than half a wingspan of a 747. We went to commercial flight, we went to space flight, we went to the moon, we've been to Mars, we've been through the solar system, and now we're getting ready to the next step, which is commercial space flight. So that's 100 years. So I think that if we think about ourselves in the 100-year time scale, we're already halfway through it. And the question is, who's going to bring us all the way through it? And I'll just tell you, what my job is, and people I work with right now, is NIF is to complete NIF in 2009, have a star born in 2010, and but you guys and gals, girls and boys, high schoolers, middle schoolers, and the like, your generation are the ones who are going to bring us a pollution-free fusion future. We're looking forward to what you do. Remember, it all comes from the sun. Our job is to bring the sun home. Okay, thank you very much.